So I'm Nick, and this is Tim, and we did our project on analyzing housing data. Next slide.
So the problem that we had was we got a bunch of housing data from a zip code in Port Orange, and we got things like the data included like their geographic location, the asking price, how many bathrooms, how many bedrooms, square footage. And it also included a living area, whether
taxes.
You could have pets. It was a lot of data. So the first thing we did was we looked at the data, and if there was ever certain columns that only had like two different things, but only one entry was different, we would eliminate it. So we cleaned up our data set just by visual inspection first, eliminating anything that had a lot of missing data or not a lot of variance in the data, and then we moved on to our next phase.
So first we conducted a regression analysis. We conducted a regression analysis for the output of sale price as well as for the output of days on market. So for the regression analysis, we improved the model by removing the variables with the lowest t-stat and then reran the analysis. So we would remove one variable at a time and rerun the regression in order to improve the model. And we stopped when we had an f-stat that was maximum. So once we removed an extra variable and then the f-stat went back down, we stopped the regression analysis. We also ran a KNN, K nearest neighbors analysis on the lat long coordinates to determine if anything in like a group of like a neighborhood had an effect on the sale price of the days on market. We ran the regression analysis in Excel because R was really finicky and kept spitting out a lot of weird errors when we tried to do it. But the KNN analysis we did conduct in R. Next slide. So here are the outputs for our regression analysis. So first let's look at sold price. So as you can see, we removed variables, and as we remove variables, this is already an incredibly high F statistic. There is huge correlation and huge deterministic probabilities in the data set to the output of sale price. As you can see, our R squared value is extremely close to 1. But as we remove these variables, you can see our f-stat went from 18,000 to 88,000. Maximizing there, it is a crazy f-stat, really high, and a really, really high R squared for the regression. Now, unfortunately, with days on market, that was not the case. Days on market provided a very poor model with the regression analysis. Our f-stat was very low, and our R squared value was very close to 0 rather than very close to 1. So as you can see the change though, as we removed variables, it did improve, but not nearly to the extent that that other regression analysis improved. Next slide. So then we used the regression analysis to predict what the sale price would be for different homes. And so we did this, and then we compared the predicted sale price to the actual sale price to get a relative error between the model and the true data. So as you can see, for the good regression model for sale price, we got an average relative error of like 0.5%, which is very low. Whereas with days on market, which provided a very poor model, you have a 90% relative error, which is much higher. Next slide.
So knowing how well the regression did for the sale price, we decided that there was no K nearest neighbors needed for that, since the regression provided enough accurate data. So instead we decided to see if the nearest neighbor would be a better predictor of how long something would be on the market, to see if certain locations sold quicker or slower than others, which is how the market is prone to be anyways. So we ran the KNN model. So what we did first was I looked at the average number of days on the market, which seemed to be about 3 months, and I divided it into 2 brackets for the KNN to compare. So it's A is more than 3 months, and B is less than 3 months for a time on the market, for days on the market, I mean. So first I ran it with a very low number of K, and you can see that the off diagonal has, there's 30 results were not accurate compared to, and then so what I did was I increased K to 17, which then got our number of off diagonal results. It's actually skewed more towards being selling in for less time. Is actually, so when the model looked everywhere, when it looked at more neighbors, it found that it was more likely that your house was going to sell more quickly than it actually would, which is interesting. But still, at the same time, there's 22 in that one and the 3 in that one, which makes 25. And when I bumped k up to 20, it only changed one number, going from a false to a true. So you can see that there's a huge increase between k equals to 3 and 17, and that's because 17 is actually the square root of our training data. So there was actually 300. There's 300 data points taken in our training data. So the square root of that's 17. So it's checking a very good amount of the data with checking 17 neighbors. And then when you go up to check 20, there's very little improvement, showing that if you increase it past the square root of the number of data points, you're not really going to get much improvement, and you're just going to make the computation time significantly longer. So in conclusion, we determined that the regression analysis was enough to predict the sales price because the f-stat was rather high. And it actually turns out that the only variable that was deterministic was the square footage, right?
Square footage and list price.
Okay, so those two variables alone gave an r-squared of 0.99 and an f-stat of 88,000. So when you're looking for houses, you can just look for those things. And then if you're looking to sell, you should look and see how long things in the area are taking to sell, rather than characteristics of your house itself. Just look at the local area, and you might get a better predictor of how long it might take your house to sell.
And that's it. Thank you.